Hello and welcome to a flipped classroom lesson on Newton's second law. Newton's second law is all about how force and acceleration relate. So we're going to start with acceleration. Little review. First of all, what is acceleration? When somebody writes down acceleration equals 5 meters per second squared, what are they talking about? Well, if we make a table of time versus velocity, for an acceleration of 5 meters per second squared, here's what it would look like. After 1 second, something's going 5 meters per second. 2 seconds, 10. 3 seconds, 15. 4 seconds, 20. As you can see, the velocity changes by 5 meters per second every second. So we can write this down as acceleration equals the change in velocity over change in time, which is 5 meters per second divided by seconds, and we can simplify the units by writing that as 5 meters per second squared. Let's take a look at a few accelerations. If the acceleration is 0, that might mean it's at rest or at constant velocity. And the constant velocity case is legitimate because if you're moving at constant velocity, then your velocity isn't changing, which means the acceleration is 0. If the acceleration is positive 2 meters per second squared, that might mean you're speeding up, going from 0 to 2 meters per second to 4 to 6 to 8 and so on, but it might actually mean you're slowing down. Suppose your velocity started off at negative 10 meters per second. Well, then you're going from negative 10, negative 8, negative 6, and so on. That's slowing down. If your acceleration is negative 2 meters per second squared, you might be speeding up or slowing down, again for the same reason, depending on what your initial velocity was, if it was positive or negative. Now, let's relate this to forces. If there are no forces acting on an object, then we know it must be at rest or at a constant velocity, due to Newton's first law. So if forces are present, then acceleration is possible. But is it inevitable? Do forces always lead to acceleration? And the answer is a big fat no. And you can see this by the simple example of a person standing on the floor. So this person's on the floor. There are two forces acting on her, gravity and normal force. Nevertheless, if she's standing on the floor, she must be at rest. These two forces exactly counterbalance with each other, and she has no acceleration. So, what do we need for acceleration? What we need is a net force. And net force means you just add up all the forces. And if they add up to anything that isn't 0, then you've got then you're going to have an acceleration. So let's take a few examples of how to add up all the forces, because it's not as simple as it sounds. It's not just the plus button on a calculator. So let's take an object, little box here, can be anything. And let's apply two forces, 3 newtons and 7 newtons. So here we go. Now, what do you think the total force is, or net force on this box? Well, you probably think it's 10 newtons, and you would be exactly correct. It's 10 newtons in this direction. Very good. You just add them up. 7 plus 3. But what about here? Now the forces are pointing in opposite directions. To find the net force, we add up all the forces, but what do we do with these opposite direction things? Well, we subtract them. So this is kind of like 7 plus negative 3, which gives us 4 newtons in this direction. 7 minus 3 is 4. Now we come over to this example. 3 newtons to the right, 7 newtons to the left. This is 3 minus 7, which gives us negative 4 newtons. What the heck does negative 4 newton means? Well, it's the same thing as negative velocity. It just means in the direction. Generalizing this, without numbers, if we have a push and some friction, we can say the net force is simply push minus the force of friction. That's our net force. Now, how do force and acceleration relate? Well, you probably suspect that if we make the net force bigger, we get a bigger acceleration. And you'd be exactly right. The harder you push, the more acceleration you get. But we're missing something, because it also depends on what you're pushing, right? What kind of acceleration you get. If you give a push to a tennis ball, you're going to get a decent acceleration. But if you give that same exact push to a truck, then you're not going to get nearly as much of an acceleration. So it probably has to do with maybe mass. So let's put all these together, force, acceleration, mass, into one equation, and that is Newton's second law. And Newton's second law states that the net force, which I abbreviate as F net, is equal to the mass multiplied by the acceleration. And this captures all of our intuitions. If we push an object with a bigger force, we get a bigger acceleration. Make sense? If we push an object with a gigantic mass, if we apply a force to an object with a gigantic mass, we must get a small acceleration, because when you multiply these two together, it must equal your net force. If instead you apply that same net force to a tiny mass, you will get a ginormous acceleration, because these two multiplied together must equal your net force. Now we can solve problems with Newton's second law, and I'm going to run through several examples of this. Let's take the easiest ones. Let's suppose there's a rock in space and we decide to give it a push, and we give it a 12 Newton push. It is a 3 kilogram rock. To solve this problem, we first write down the equation we're going to use. That's always a good strategy to start with. We write down F net equals ma, saying, hey, I know this is a Newton's second law problem. Then we plug in what we know, the force, the mass, and then we solve it. Now, you're supposed to plug in all the forces added up, but we've only got one force, which is 12 newtons. So this is pretty simple. Now let's do a little harder one. Somebody's pushing a cart along on Earth when there's no friction. In this case, we have to draw a free body diagram, and there's more than one force. You've got a push force, which is 50 newtons, and you've also got gravity and normal force. But gravity and normal just cancel each other out, since the block isn't moving up or down. So the only force that's left is this 50 Newton force. So we write down F net equals ma, we plug in for F net, which is only 50, and then we plug in for our mass, and we solve for our acceleration. Now, let's do another example, a little harder one. On Earth, Sarah pushes a 200 kilogram box with a force of 150 newtons. There's 100 newtons of friction. Calculate her acceleration. So we draw the free body diagram here. And I drew in gravity, normal force, which cancel. There's her push. There's her force of friction. Now I suggest we use F net equals ma, so I write down the equation. Now, I know that F net is just push minus force of friction, and that equals mass times acceleration. I haven't plugged in any numbers yet. That's a strategy I'm using here. Save the plug-in numbers for later. Just write this down here, no numbers. Now, when I've got this equation, I plug in what I know, push, friction, mass, and now all I have to do is solve a simple linear equation and do some math, and I get my answer. All right, here's one for you with a twist. Sarah pushes a box with a force of 80 newtons. A friction force of 20 newtons is present. The box accelerates at 0.2 meters per second squared. I want you to calculate the mass of the box. Take a moment, see if you can do this one. Pause the video. Let's see how it's done. So we draw a little picture of this. You've got normal force, gravity, push, force of friction. Of course, gravity and normal force again cancel out. They don't always cancel out. If something's on a string, they're not going to, but here they are. Write down F net equals ma, push minus friction equals ma, and then we plug in what we know, and we solve for the mass. And we get 300 kilograms. All right, time for a nice hard one. So another box pushing one. Sarah pushes a 150 kilogram box with a force of 300 newtons. It accelerates at 1.5 meters per second squared. Friction is present. Calculate it. Well, same strategy. Draw a picture. Free body diagram. F net equals ma. Push minus force of friction equals ma. I got a little overzealous plugging numbers in here. Now, I plug in everything I know. Push minus force of friction equals ma. Push is 300. Friction's unknown. I know the mass and the acceleration. They multiply to 225. All I need to do is solve for the force of friction. We got it. That wasn't so bad. Now, let's take a look at some of the lessons that we've learned. F net equals ma is a bit of an interesting equation because you kind of have to make your own equation. You see, m and a are easy. They're just numbers. But the F net, you have to cook up yourself. And it depends on what forces are actually acting on the object. So you kind of have to make your own equation there. When you're solving a problem, you should follow these steps. First, draw a picture. Then draw a free body diagram. That means drawing all the forces. Use F net equals ma with no numbers. Just write down all the symbols and all the names of the forces, but don't plug any numbers. Then finally, plug the numbers in, and you should get an equation that you can solve mathematically. Just solve it like you would in math class. I'll end with a trick question. I call this a trick question in quotes because, it's not really a trick question. It's a question that I expect you to be able to do. But it does involve a twist. Here goes. Sarah pushes a 50 kilogram box with a force of 200 newtons. It travels at a constant velocity of 2 meters per second. Calculate the force of friction. So, take a moment to do this. Okay, so if you've done this one here, my guess is that some of you will have gotten an answer of 100 newtons. And that is completely wrong. I'm so sorry. It is not 100 newtons. Let's do it out.
There's our box. Gravity. Normal force. Push. Force of friction. Right? Familiar. F net equals ma. Push minus friction equals ma. So far so good, right? We're all in agreement, I hope.
Now, we know let's plug in some numbers. We know that our push is 200 newtons. Our force of friction is unknown. Our mass is 50 kilograms. And our acceleration is 0. Yes, 0. Because it's traveling at a constant velocity. That means it's not accelerating. This number here was completely irrelevant. It's a red herring. Because there's no velocity in this equation right here. You put in the acceleration. And then we solve our equation, and we get force of friction equals 200 newtons. All right, and that wraps up our video.